In this video, we're going to be designing a successive loop closure control for our lateral dynamics. What that'll do is it'll allow us to control our course angle with an inner loop of a roll angle and the outer loop of a course angle. And it'll also allow us to do yaw dampening. So let's go ahead and get started. So when we come in and we start to look at designing our controls, we see that we have augmented our plants that we developed in Chapter 5 with these feedback control terms. And to control our course angle, we'll take a desired course angle, and we'll do that. We'll put the superscript C to denote that that's going to be our controlled value. And we have a transfer function from our desired course angle all the way to our course angle itself. And then we'll also use a desired roll rate of equal to 0, and we'll use that to allow us to have a yaw dampener for the other part of our lateral autopilot. One thing to note here on the upper autopilot component is that we have this inner loop. So again, we're using that successive loop closure where we're going to design the control for our roll, and then we're going to design it in such a way that it looks like we have unity gain for the outer loop. So let's go ahead and we'll jump into that roll control. So for our roll autopilot, we can look at this and see that right here, this was the plant that we had from Chapter 5. So we developed this transfer function in Chapter 5. And then we're coming in here and we're adding this control loop onto it. So this is our new control loop that we're using for this inner control. And we can tell that it's an inner control because we're actually using, choosing the control, the actual control being applied to the system. So here we have our aileron command. So if we take a look at this, our aileron command is going to be equal to, we have this Kp sub phi multiplied by our desired control value, or our desired value for our roll angle, minus phi. So we have a proportional gain on the error of our roll angle, minus, then we have a derivative gain multiplied by p, where we talked previously that p is almost equal to the time derivative of phi. In fact, we'll end up having plus some disturbance is what we put in there. So we have p is nearly the time derivative of phi, and so this is just a typical PD control. Okay, so in our PD control, we have to choose what our values, choose what our values for these gains are going to be. But if we notice that the resulting transfer function is a second order transfer function, the book goes through a process of designing these control laws in terms of the natural frequency and dampening ratio of the desired natural frequency and dampening ratio of our transfer function. So these are desired values, or maybe we could write it as characteristics. So we have a desired natural frequency and a desired dampening ratio. And from these desired values, we can then directly calculate what our gains are going to be. So if we choose our gains as given, then we'll end up getting the natural, or nominally get the natural frequency and dampening ratio that we want. Okay, now there's one more thing that we need to be very careful about. And this is the only time we'll mention it, but do note that there's going to be several times where we have a subtraction. Our error term is defined in terms of angles, right? And so this error right here, this is defined in terms of angles. Oops. In terms of angles, huh? Angles. Okay. So the issue we have is if we were to draw out an angle, we know that this angle right here corresponds to a value of 0. Go up, this angle would be pi halves. If we go all the way around, we have, or 3 pi halves going to pointing down. And then if we go back, we get a 2 pi. So in other words, as we're moving around here, the angle that corresponds to 0 radians is the same as the angle that corresponds to 2 pi radians. So we have to be careful with this. If we have our error in terms of phi is equal to the desired control value minus our actual value, and say that phi super c is equal to pi, and that phi itself is equal to negative pi, then our error, I don't know why I crossed that off, is equal to pi minus a negative pi, which gives us 2 pi, right? So our error should be 0, but it actually looks really big. So we need to make sure we correct. So we correct or wrap our error term such that it belongs in the set negative pi to pi. And if we do that, then we won't have any issues. So we just need to be careful when we're doing subtraction of angles, because they look like they're in the real numbers, but they're actually in the set of spherical numbers. So where 0 is equal to 2 pi. So just convert your angles so that, convert your error term so that wrap it around so that it's between negative pi and pi. Excellent. So another thing you'll notice up here is that we have a PD control, right? And I wrote that here. We do not have an integral term. And integrators add delay, and they can add instability. So that's not ideal for the inner loop. Instead of correcting steady state errors in the inner loop, we're going to allow steady state errors to be corrected in the most outer loop. So we don't include an integrator until we talk about the coarse angle loop. So that's just something I wanted to point out. We only have PD on that inner loop. Okay, and then once we've designed that control, like we've mentioned before, to the outer loop, the inner loop looks like a pass-through. Meaning that it's so responsive compared to the responsiveness of the outer loop that it looks like it commands this phi super c, and it is immediately achieved in terms of what the outer loop cares about. So that's the idea of successive loop closure, right? So we have these successive loops where the inner loop now looks like a pass-through. Okay, so we have now we're going to design our coarse hold loop, where again we have this phi super c, and it looks like basically just our pass-through, right? So let's design what that phi super c is going to be. If we take a look at this block diagram, we see that this term right here, this is our integral term. So this is where we end up getting our integral. So we have our phi super c is equal to the ki sub g times the integral from whenever we started to the current time of, and if we look at what this term is, that's our error sub g, but that's just going to be our coarse angle that is commanded minus the coarse angle, the current coarse angle. So that's the top component, our integral component. And then we also just have a proportional component, kp sub g, where we again are doing that on our error, so we have minus our chi. So this is the controller that we're realizing. Okay. Now, if we form the transfer function, we still have a second order system. But the problem is now we have a 0 on top. And that does change things just a little bit in terms of the response of how we can interpret what the damping ratio is going to be. Okay, so but the presence of the 0 at the origin would ensure rejection of low frequency disturbances. Okay, so here's just a look at some Bode plots. And again, we have this 0 up top. And we note that that there is a slight difference in our response when we have that 0 present. But we can still get, we have something that's close to, this is what we wanted, right? So this is what we want, and it does provide at least a good starting point for how we're going to be designing our system. So again, we have our control, and we have our natural frequency, and we have our damping ratio. And if we have those, these are defined for us. So if we given our natural frequency, our desired natural frequency, and our damping ratio, we can then calculate our gains. So we can, if we know what characteristics we want our system to have, then we can immediately calculate that proportional and integral gain. So that's the whole point of this slide. With one other caveat is that we don't choose the natural frequency independently. So we choose our Wn sub chi based on Wn sub phi, right? Because our outer loop has to be less responsive than the inner loop. And so we're going to, this W sub chi is going to be on the order of 10, somewhere between 5 and 20 is what the book recommends. But we have, so we define the natural frequency for this outer loop based on the natural frequency of the inner loop. So that's important to know. Excellent. So the final thing on this, let's see, make sure I didn't miss anything. The final thing on our course hold loop is that we typically want to add a feed forward term. So I'm going to rewrite the control. Our commanded value for phi, again, is going to be equal to the ki sub chi times the integral t naught to t of our commanded value for our course angle, minus the actual course angle, plus a proportional term, and that proportional term is based on that same error signal. So we have that control, and nothing's different here. But when our course heading is achieved, then our error goes down to 0, right? So this term right here we called our error sub chi. Okay, so when our course heading is achieved, that means that that error is equal to 0. Okay, so now if our integrator had caught up and say that this integrator term is equal to 0, and by proportional, we were able to just get there really quick, we'll end up having 0. That'll say that our commanded value for phi will go to 0, right? But that's not necessarily what we want it to do, because when we do a coordinated turn, want a constant value for phi. Now, we can actually have our if we run it just like this, our integrator will eventually learn the steady state offset that is needed. Value of phi that is needed. So if we're in the turn for long enough, or if our integral is strong enough, then we will end up having, we will end up reaching that steady state of value for phi eventually. But why wait for the integral to learn when we already know about coordinated turns and we can get a really good estimate for what that value of phi should be in order to keep in that turn? So instead of waiting for the integral to learn, we can use a feed-forward term that we calculate using our coordinated turn. So in other words, what happens is I'm just going to write it in green up above. So we'll do our phi sub c is equal to plus. So we're just going to do this right here. We're just going to pass in a feed-forward term. So we already know that we have a desired value for a feed-forward, or a desired value for phi. Sorry, let's just pass it in as the basis for our command, and then we'll let the integral adapt from there. Okay, so that'll allow us to do our course. That'll finish off our course angle loop, and now given a commanded value for our course angle, that'll allow us to achieve it. And we saw that in the simulation, which was pretty cool. Okay. So the other part of our lateral dynamics, or lateral control, is that we're going to add a yaw dampener. And if we look at this control right here, all this is just a derivative with a low-pass filter. Okay, so it won't get all the high frequency content that's coming from our roll rate, which is good because that can be quite high frequency. It can have a lot of decent amount of noise in it. So we filter it, and then we just do a gain on that, and all we're doing is we're adding dampening to our roll rate. And again, this is known as, this type of a derivative is just a dirty derivative. So it helps us counteract the adverse yaw effects. Okay, so to summarize our lateral autopilot, for our inner loop, we'll have a given value for our natural frequency and our damping ratio. These together will help us choose our K, P phi and our K, D phi. So that gives us an initial choice for those gain values. Then our outer loop, we'll get our omega chi natural, is going to be 1 over Wx times our natural frequency of the inner loop. So we have that the inner loop and the outer loop are dependent on each other, or the outer loop is dependent on what the inner loop is. Okay, and then we can also define our damping ratio independently, and those will give us our Ki sub chi and our Kp sub chi. So by defining those parameters, we can get our initial values for those control gains. And for our yaw dampener, we can define our cutoff frequency for the washout filter and a gain for that yaw dampener. And then if we're going to tune this in flight, so our dynamics will be slightly off, model not known perfectly, we can take those original values that we have, and then we can start. This just gives us some instructions for how we would get to an acceptable steady state response. Excellent. So given that, we now have autopilot capabilities for our lateral variables.